okay? And each carbon atom is sp2 hybridized. The 3 sp2 orbitals lie flat on the plane of the benzene ring, and then there is a p orbital for each carbon atom. Each carbon atom will only have one p orbital, and inside this p orbital there is one electron. So since there are 6 carbon atoms, there are 6 pi electrons, and 6 pi electrons can make 3 pi bonds, with each bond having 2 electrons. Okay, so the delocalized system, because the p orbitals are parallel to one another, but it is perpendicular to the benzene ring. I hope you know the difference. Okay, now because they are parallel together, they align next to each other, so the electrons actually can move from one orbital to the other, and not only on the top part but also on the bottom part. So that's why you see this delocalized system, which looks like a ring, like a donut, on above and below the plane of the benzene. So you can imagine benzene as being a molecule with rich electron density, high electron density. Okay, the shape of a benzene molecule, you have to look at each carbon atom first. Each carbon atom has 3 bonds or 3 electron density around it. And you know that when you have 3 bonds around a central atom, it will take the shape of trigonal planar. So since each carbon atom is trigonal planar, overall your benzene molecule is a planar molecule. That means it's just a flat molecule, no 3D, no bonds coming in and out when you draw it. Okay, so that's the ring of delocalization, top and bottom. Now we're going straight to naming. Okay, so we name the simpler molecules first. Usually the simpler molecules are the ones that end with benzene. So the first one here, CH3, is a methane. So methyl is the side chain. We call this side chain or side groups. Okay, anything that is hanging off your main molecule, we call it a side chain or side group. So it's called methylbenzene. Please write this down in your notes. I think your notes is empty. The next one is C2H5. That's quite obvious. It's called ethyl because 2 carbon, ethane, so ethylbenzene. Cl is a chlorobenzene. Br is a bromobenzene. And O2 is a nitrobenzene. Okay, the next one is the COOH, which is a carboxylic acid. We call it, you may have heard of it before or may not, we call it a benzoic acid. Okay, so that's a little bit different where it doesn't end with benzene. Okay, so please make sure you copy this down. Who am I missing from the session? Kawi, is it? Yeah. Okay, moving on. CH2Cl. CH2Cl alone is called a chloro if there is a chlorine in a 1 carbon atom. We call it chloromethane. Okay, so here we call it a chloromethylbenzene because there's chlorine, there's 1 carbon which is of a methane. Okay, the next one is an ester. I don't know if you noticed this or not. It is a C double bond OC, COOC. Okay, when naming an ester, the alcohol bit comes first, ends with YL. So in this case, it's 2 carbon membered, so it's an ethyl. Okay, and then the other side is your carboxylate, which should end with ATE. So we call this an ethyl benzoate, and that is an ester. Okay, moving on. This time, the benzene ring can be represented or as a substituent side group. Okay, so now benzene is no longer in the principal chain. Okay, when it becomes a side group, we call it the phenyl. Okay, not benzyl, we call it phenyl. So that's something new for you to remember. Okay, when you have a benzene with an OH, this is like an alcohol. The name is phenol. Okay, it's not I don't know, methanol, benzene or something. How do you know these names? Well, you only know it as you go along. It comes with experience. If that name sounds familiar to you, then it should be correct. If it doesn't sound familiar to you, then maybe it's not correct. Okay. The next one, NH2, it's called phenylamine. Okay. You've already come across a functional group. Well, briefly, anything with NH2 is an amine. Ethylamine, methylamine, butylamine, and etc. So now it's phenylamine, not benzylamine. Okay. Do not confuse NH2 with NO2. NO2 is a nitro. NH2 is an amine. Now you have an ethene. Okay, so we call it a phenylethene. The next molecule, your principal chain is the alkane. 1, 2, 3, 4. So that's butane. Hold on. So we call this 2-phenylbutane. Now, what's the difference between 2-phenylbutane and ethylbenzene? Ethylbenzene, the benzene is in the first carbon. Okay, but when you start moving the benzene in these positions, whether you go to the second, well, you only have two. The only possible position is first carbon or second carbon. Now, because you are in the second carbon, that's why we say that the benzene, the phenyl group, is now the side chain. Okay, so your principal chain is 1, 2, 3, 4, butane. Next, C double bond O, C, C. I hope you remember that that functional group is of a ketone, phenylethanone. Ethanone, because you have two carbon, and then that other side is the phenyl of the phenyl means benzene. Okay. Next one is also an ester, COOC. This time the benzene, the phenyl, is the alcohol part. Okay, and then this is the carboxylate part, which is the ethanoate. So we call this phenyl ethanoate. Okay, I'm just going to go really briefly without much explanation on this. Next, what if you have more than one side groups on your benzene ring? So the first example is here, you only have one side groups, right? So automatically, when you have that side group, the carbon automatically becomes number 1. Okay, and you don't have to number them. You can number them 1-methylbenzene, but you know, it's everyone understand it. Okay, if you only have one side group, then that side group should be sitting on carbon number 1. Even this one, even if you draw it like this should be carbon number 1. Okay, yeah, right. Next, where was I just now? Okay, this one, right? So naming this, you have to take your principal group. In this case, your principal group is a methylbenzene. Okay, so methylbenzene is your principal group, or as we call principal chain. That means your chloro is your side chain. Numbering this, 2-chloromethylbenzene. Nick, why do I have 2 Nicks? Nick, is that you on another device, or is that you know, someone pretending to be
Yes,
Nick.
miss. Yes, miss.
It's you. Okay, I will accept. Right. So 2-chloromethylbenzene. Methylbenzene automatically, this carbon, the one where your methyl is sitting on, is carbon number 1. Okay. Numbering system, you could either go clockwise or anti-clockwise, and you always take the smallest number. If you go clockwise, chlorine is number 2. If you go anti-clockwise, chlorine will be 6, carbon number 6. So you don't want to call this a 6-chloromethylbenzene. Okay, the naming rule is exactly the same as the ones that we have covered in AS. Okay, we want to take the position that gives the lowest possible numbers to the substituents. Substituents like this, the chloro is a substituent. Okay, next, again, your principal chain is a methylbenzene. How do you know that? Well, just from experience. Okay, so in this case, your chlorine is 3-chloromethylbenzene. Either you call it 3-chloromethylbenzene or 5-chloromethylbenzene, but 5-chloromethylbenzene is wrong. I mean, it's not the lowest number. Okay, so this one automatically becomes number 1, 2, 3. Okay, if you start counting from the left, then you will get chlorine to be sitting on carbon number 5. Next one is 4-chloromethylbenzene. I missed an E there. Okay, so your principal chain is your methylbenzene. Okay, the next one, your benzene is the principal chain, and you have 2 methyl groups, dimethyl. Numbering them, well, you can choose either one. If you call this number 1, the other one will be number 3. Okay, do not take it as 1 and 5 because there is a smaller number, 1, 2, 3. If you want to take the other, the bottom one to be number 3, it will give you the same answer. Okay, this is called a 1,3-dimethylbenzene because you have 2 di, okay, 2 methyl groups. Now the other numbering system is if you take this bottom, if you take the bottom right methyl group to be number 1, same thing also. This will become number 3. So it's still 1,3-dimethyl. Okay, do not call it number 5. Always take the smaller number. I hope we're doing okay. Next. If 2 or more substituents are present on, okay, same thing. Okay, this time your principal chain is this. Benzene with an OH. If you go back to the previous part, benzene with an OH is called a phenol. Okay, so phenol, automatically the OH becomes number 1 because it is the principal chain. So 2, 4, 6. Even if you go in the anti-clockwise direction, you will always also get 2, 4, and 6. Okay, 2, 4, 6 tribromophenol. Phenol is your principal chain. Next, COOH and OH. So you have to decide who is the principal chain. COOH is your principal chain. Okay, so this is something benzoic acid. So when you have an OH as a side group or a side chain, OH is called hydroxy. So it's called 4-hydroxy benzoic acid. The carbon in the COOH, this will become the first carbon. Okay, the carbon that is attached to the COOH becomes the first carbon. So in this case, even if you take anti-clockwise or clockwise, this carbon will always be number 4. Okay, sometimes clockwise, anti-clockwise direction will give you the same number, but sometimes it will not. Okay, and then that tells you the next one, between the carboxylic acid and the nitro, the carboxylic acid will become your principal chain. So because that is a principal chain, that automatically becomes number 1. So your nitro group is the one hanging off as the side chain. So nitro is position number 3. Right. Right. Undo. Okay, so this is the 3-nitrobenzoic acid. Are we okay? Am I going too fast? Well, I intended for it to be fast because it's just naming. Sometimes they ask you quite straightforward namings, but so far there's nothing really complicated that they would ask you. Well, so far. Right, moving on, which is the more important bit of today's lesson, is to look at the chemical reaction of benzene. So that is looking at the mechanism. But first, let's just recall back the background of benzene. So benzene is rich in electron density. There is a rich electron density above and below the plane. So that means they attract electrophiles. If you remember, electrophiles are species that accept electrons. So benzenes will give the electrons to the electrophiles. Benzene does not generally undergo addition reactions, okay? Because addition reactions would mean that you are breaking up the delocalized system. Unlike an alkene, they undergo addition. Both alkene and benzene attract electrophiles because they have rich electron density above and below. For benzene, it's above and below the plane. For alkenes, it's above and below the double bond. Okay? However, the only difference is alkene goes through addition, benzene goes through substitution because the delocalized system in benzene is stable. They do not want to lose it. Okay. If you start adding, if you look at benzene, the structure of benzene, the carbon can only have, each carbon can only have one thing hanging of it. Okay, so it's a hydrogen. If electrophile comes in, obviously you need to kick out this hydrogen. Okay, you cannot have this hydrogen anymore. So that's why if you look at this benzene, these molecules, each carbon in the benzene ring can only have one thing hanging of it. It may be a long chain, it may be a short chain, but only one carbon hanging off. If you have more substituents, it will be placed in a different carbon atom. Okay, this is because of the fact that the delocalized system is stable. Right? So the characteristic reactions of benzene rings are electrophilic substitution. Okay, so I am going to use another device, which is the one that I use for drawing. Oops. Hold on, just bear with me. Which is my iPad. Okay, can you see this? Where it says recapping?
Yes.
Okay, right. So just to recap, the mechanism of alkenes, some of you will may have thrown this out of the window already, thinking that, you know, don't care, right? But just a quick recap. So the double bond of your alkene is the one that attracts the electrophile, and it donates one of the double bond breaks. Okay, so it attacks the electrophile, right? Now, there are two possible carbons where the electrophile can sit, carbon on the left or carbon on the right, okay? It doesn't matter, at this point it doesn't matter because your alkenes is a symmetrical alkenes. If you have an unsymmetrical alkenes, this is where your Markov-Nikov rule comes in. That's not an alien language. Markov-Nikov is something that you have learned last year, okay? So if you don't remember what that is, I suggest you to revisit your alkenes notes. Okay, so I have written it so that carbon on the left, which is carbon 1, and carbon on the right, which is carbon 2. Okay, my electrophile sits on carbon 1, this carbon. Okay, now if you look at this carbon, there are 4 bonds around it. 1, 2, 3, 4. Happy. Okay, the other carbon only has 3 bonds. That's why it has the positive charge. Okay, also, if you still remember this fact, where if you break a bond heterolytically, okay, like that, in this case, A will become positive, B will become negative. Okay, so whoever gets the electrons will be negative, and whoever doesn't get the electron will be positive. So in this case, electrophile, oops, I should not do that. Electrophile gets the electrons, so positive, negative cancel out. Okay, this carbon doesn't get anything, so that's where the positive charge is. Right. The next part, to stabilize this positive charge, because positive charge carbocation ion is an intermediate. Right. So comes in a nucleophile. A nucleophile is a species that can donate electrons. In this case, it's a bromide. A bromide ion. Well, so far this is the example that we have been using. So bromide ion has that lone pair of electron to be donated to the positive carbocation ion. Okay, so you can see that the positive and the negative charge will cancel out to become neutral, forming a carbon-bromine bond. Okay, that's alkene. Oops. Ayo, who is sneezing? Next. Now I'm going to compare alkenes and benzenes, the reaction of alkenes and benzene. Okay, so this drawing is using the calculate structure. If you notice, there is an alternate double, single bond, which is the calculate structure, which is not the structure that we tend to use in our syllabus. But I'm going to draw that first so that you can see how similar it is with the double bond in alkenes. Okay, was that Ang who sneezed? This is why we have online classes, right? So you can sneeze all you want, but you will not infect any of us. Right, back to this mechanism. So I've already highlighted that for alkenes, it's an electrophilic addition. For benzene, it's an electrophilic substitution. Okay, so first things first, for benzene, you have 3 possible, you have 3 double bonds, which is according to calculate structure, which we know that is not accurate, but I will just draw it. So you can choose any of these 3 double bonds. Okay, for me personally, I like to use that top right double bond. Okay, just personal preference. Same thing, the double bond, which is rich in electron density, will attack the electrophile. It donates its electrons to that electrophile. Okay, so now my electrophile can choose to sit on, let's see, let me write. This is carbon number 1, this is carbon number 2. Should have used a different color. By the way, I really like this app. It cost me $7 US, $8 US, $7.99. Okay, so that's carbon number 1, carbon number 2. So when that double bond attacks the electrophile has an option to sit on carbon number 1 or carbon number 2. In this case, it does not matter. Okay, it's called good notes. Right, so 1, 2. Okay, the way that I have written it down is that I put my electrophile to sit on carbon number 2. Why? Just because I like that position. Okay, so electrophile sits on carbon number 2. So this carbon here has 4 bonds, if you can see that. Okay, the other carbon, which is carbon number 1, has only 3 bonds. And if you compare this carbon that has 3 bonds with the carbon on the alkene, it's the same carbon, right? Carbon with 3 bonds is the one that develops the positive charge. Okay, right. So now I want to make the positive charge happy. I need to give some electrons to it. To cancel out a positive charge, you need some negative. Okay, that negativity doesn't come from an an external nucleophile. What I can do is the carbon-hydrogen bond that I had originally can be broken down, okay, and the electrons from that bond can be donated to that positive charge. Okay, so the negative charge on the electrons and the positive charge on the carbon cancel each other out to get this product. Okay, so this is how substitution works, and this is how addition works. I hope you can contrast between these two. Okay, that is when we draw calculus structure, which is not recommended. Okay, now if I try to draw it using the benzene structure that we understand, which is this, a hexagon. Hey, boys, please, I'm not asking you to promote this app. Listen. Okay, so the bottom mechanism is the one that you are recommended to draw. Okay, you draw a hexagon ring and then a circle. Remember that each carbon has a hydrogen. It's just that I haven't drawn it. Okay, same thing. Okay, so there's a only slightly different from the calculus structure. Okay, the calculus structure, you see exactly where the double bond is, but for the delocalized system, delocalized structure, you guys are distracting me. For the delocalized system, there isn't a specific position of the double bond. Okay, so we have 10 minutes left, so I'm really gonna rush through this. Right, I've numbered my carbon atom. 1, 2, 3, 4, 5, 6. I don't know if you can see it. I hope you can. But this app lets me zoom in into the structure to write even a smaller writing on it. Okay, so that's one of the reasons why it's great. Right. Okay, so I start attacking from the circle inside the ring because that's where my delocalized system is. I don't have to worry where my double bond is, but I know I am affecting the double bond between carbon number 1 and 2 because you can see my arrow is between carbon number 1 and 2. So that means my carbon number 1 and 2 will be affected. Okay, so the delocalized system will break. Okay, it attacks the electrophile. There should be a positive charge here that I have missed out. So again, because of personal preference, I like to put my electrophile on carbon number 2, just because. Okay, so that means my positive charge is on carbon number 1. Okay, by right, it's on carbon number 1. However, the positive charge is being delocalized. Okay, it is being spread out to everyone. That's why you see my positive sign in the center. Okay, another thing is to show the delocalized system. Okay, I will draw from 6 to 5. Is it that? Yeah. Okay, my delocalized system is now from not 6 to 5, 3 to 6, 3, 4, 5, 6. Okay, because all my system for carbon 1 and 2 is kind of broken. Okay, right. So in order to restore, do not forget on carbon number 2, I have a hydrogen. Actually, on each carbon, I have hydrogen also. Okay. So now I want to restore that delocalization because delocalization is stable. The only way to restore it is to break the carbon-hydrogen bond. Okay. The electrons from the carbon-hydrogen bond is donated into the temporarily broken delocalized system. And then you see in the product, the hydrogen leaves as H+. Okay, and the delocalized system or the delocalization is restored back to normal. Okay, one thing that I forgot to mention is when the carbon hydrogen bond breaks, you are releasing H+. You are letting go of the H+. Okay, if you don't let go of the hydrogen as a H+, that means you have 2 bonds on the carbon. Then that's not that won't give you the delocalization that we have in a arene or benzene ring. Okay, now you notice that initially I started my numbering system with 1 on top. In the product, obviously now the numbering system changes. Wherever your electrophile is sitting, that becomes automatically number 1. Okay, is that clear? Now you have 6 minutes left. So I want you to read this. Right? This is the general mechanism for an electrophilic substitution reactions that you have in your notes. So the way that it's written, drawn in your notes is that the electrophile sits on, the electrophile sits on carbon number 1, okay? The broken delocalization system is important for you to take note that it extends from carbon number 2, 3, 4, 5, 6, okay? Okay. Okay, so that means I have drawn it inaccurately here. Since the electrophile sits on carbon number 2, the broken delocalization should extend from carbon 1 to carbon 3. Where's my, here, okay. You see that electrophile sits on carbon number 2, right? So my broken delocalized system should extend from carbon 1 to carbon 3, okay. Okay, going back. Right? Electrophile sits on carbon 1 to restore the delocalized system. The carbon-hydrogen bond has to break and donate its electrons to cancel out that positive effect. It's an intermediate only, okay? And then you release, carbon-hydrogen bond breaks, and then you release the hydrogen as H+. Okay. Some of the things that I want you to take note of, we have 4 minutes left, okay? In this case, here, all your carbon 1 to carbon 6, they are all sp2 hybridized. Okay. In the intermediate, this is a very unstable intermediate, as I said, because you're breaking the delocalization. Delocalization is a stable system. So carbon 2, 3, 4, 5, and 6 are all sp2 hybridized. Carbon 1 has 4 bonds, 4 single bonds at the moment. So it is sp3 hybridized. Okay, so please take note of this, that carbon 1 is sp3 hybridized while the rest are sp2. Because in the intermediate, only carbon 1 has 4 single bonds. Everyone else has 3 bonds. Okay. So carbon number 1 has a bond angle of 109.5 instead of 120 degrees. So once you change the hybridization of the carbon, the bond angle will also change. What else do I want to point out here? The pi bonding extends over 5 carbons, okay? That is the 5 carbons where your electrophile is not sitting on. So I repeat, here your electrophile is sitting on carbon 1. So that means your delocalization is only from carbon 2, 3, 4, 5, and 6. That's why carbon 2, 3, 4, 5, and 6 are all sp2 hybridized still. They are, in a way, they are still, you know, agreeing with the delocalized system, except carbon number 1, which is sp3. Okay. Any questions before we go? You have 2 minutes left to ask me questions. This is still the general mechanism, okay? We use E as an electrophile. Any questions before we go?
No.
Can understand?
Yes.
Really? Wow.